this is about module 3 microfabrication for micro robotic system. We have discussed the different types of microfabrication techniques which are available, like we had talked about this bottom up approach and top down approach, and the different kinds of microfabrication techniques which are involved in bottom up approach and top down approach. In fact, in the last class we had discussed about this plasma processing, about the different types of plasma processing. So as far as this plasma processing is concerned, the plasma processing, as discussed earlier, it is mainly meant for realizing the surface with reference to the functionality. So a plasma treatment is a powerful surface modification technique which is used to tailor the wettability of polymers, enabling the transformation from hydrophilic to hydrophobic state. This process is particularly beneficial in applications such as biomedical devices, coatings for micro-robotics and microfluidic systems. So if we try to classify this plasma processing based on the mechanism of surface modification used in plasma processing. So based on the surface roughening process, we can classify. Based on the chemical functionalization, we can classify. And then based on cross-linking and surface coating. First, let us discuss about this surface roughness. So surface roughness is nothing but, so we create a roughened pattern or a nanostructuring structure so that the plasma etching creates a micro and nanoscale roughness, enhancing the hydrophobicity. So ideally, in order to generate such kind of roughness, a high energy plasma generated by oxygen, argon or CF4, which is selectively remove the surface layers to generate such kind of microstructure, to generate such kind of textures. Basically, it might be a microstructures or it might be a nanostructures. So when such kind of textures are generated, it will be helpful for us to repel the water so that it has a potential application in underwater related micro robotic systems, or even it can be used for biomedical related micro robotic system. Another technique which is involved is called as a chemical functionalization. As far as this chemical functionalization is concerned, the plasma treatment can introduce or remove the functional group that influence the wettability. So the hydrophobic transformations, that is a fluorine based plasma deposits a fluorocarbon group and reducing the surface energy. The hydrocarbon plasma creates a hydrophobic polymeric coating on it. So through this particular process, we can have a kind of an hydrophobic transformation in this system. Next, when we try to talk about cross-linking and surface coating, plasma polymerized thin films of fluorinated or silicon-based coating enhances the long-term hydrophobicity. So it's a kind of a plasma-assisted grafting of low-energy polymers such as PDMS or Teflon-like coating, basically reduces the water adhesion on the surface. So these are some of the different plasma processes which are being effectively used to protect the device or to improve the functionality of the devices based on the requirement or based on the different functional applications. Now, let me introduce you to a new technique where a 3D printing is used for fabricating a micro features or micro devices based on the requirement. So as far as 3D printing is concerned, we all are aware about it. Almost last 3-4 decades, there is a huge evolution in the field of additive manufacturing and 3D printing. So in most of the cases, when we try to talk about 3D printing, feedstock plays a vital role. So feedstock is nothing but the raw material. Based on the raw material, normally we select the type of 3D printing or additive manufacturing process for different applications. So one is through the feedstock, another one is through the manufacturing geometry, features and overall process capability. Now, these kind of parameters are well established with reference to a macro level perspective point of view. However, there is a need to establish a micro level based 3D printing technology so that it has a potential application in printing micro sensors, micro actuators, and micro features, etc., for different applications. Now, the main focus of this particular topic is to discuss the different technologies which are being evolved with reference to this micro 3D printing, so that it's a kind of a small, creating a small scaled features based on the requirement and based on the practical applications. Now, as far as this micro level printing is concerned, these micro level printing are classified into two. One is called as non-laser based printing, another one is called as laser based printing. So, as far as in this non-laser based printing is concerned, we can classify this non-laser based printing at different categories. So, one is called as a micro contact transfer printing, that is, we use two layers. So, in one layer there is a kind of a printed structure. Through a kind of a compression, one set of features is being transferred to the next layer. Next is called as a nano imprint lithography. So, this nano imprint lithography process is concerned. So, in this particular process, so what we try to do is, like, we can print the structures on pixel by pixel region. In fact, regarding lithography we had discussed in detail, and there is a kind of a capillary force lithography. So, this capillary force lithography is mainly meant for transferring the liquid or gel based structures to print different features. Stamp assisted transfer printing is almost similar to a micro contact printing, where two mask based structures are brought together, and through a compression that features are transferred from one substrate to the other substrate. Then we have an electrostatic transfer printing. So, this electrostatic transfer printing, we all are aware about it, the photocopying machine. So, the same technique is evolved to print on the flexible substrates, to print on flexible PET sheets, or to print micron level layers on any kind of structures, etc. Now, when we consider a laser based printing, this laser based printing is classified into two. One is called as non-laser decal transfer based printing, and the other one is called as laser decal transfer based printing process. So, before going into this non-decal transfer based printing and laser decal transfer based printing, both these printing has an advantage where we use feedstock in the form of thin film. And one of the key motto of this particular technology is to avoid mask fabrication, and we can directly print the features based on the requirement. So, it's a kind of a maskless printing, which is promoted over here. So, the main motto of this maskless printing is, like, we can align the mask. So, by aligning the mask, here normally what happens is, in most of the cases, manufacturing the mask itself charges a lot, and in certain cases where, like, even for 8 to 10 micrometer we may need to manufacture a mask. So, these can be completely eradicated. These process has a capability that up to 1 to 2 microns we don't require a mask. So, anything below 1 to 2 microns can go for a lithography process. However, between 1 to 2 micron, this has a capability to directly print the structures. Now, let us see the overall principle of this non-laser decal transfer and laser decal transfer. So, as far as in this non-laser decal transfer is concerned, so let me just introduce you to the component. This is called as a donor substrate and the donor material. So, the donor material is nothing but the material which we are planning to print, and the acceptor substrate is the substrate on which we are planning to print the structures. Now, what we are trying to do is, so this is a kind of a thin film which is going to act as a feedstock. The laser beam is made to pass through this donor substrate, which is transparent to the laser beam. However, when it interacts with the donor material, this donor material gets transformed in the form of a micro droplet. This micro droplet will get ejected from the substrate as shown over here, and it sticks on to the acceptor substrate. And continuous transfer or continuous interaction of the laser with such kind of micro droplet will result in a droplet ejection, leading to a kind of a pattern what we are looking for. Now, in this particular aspect is concerned, one of the key point which we may need to note down is, like, the droplet ejection. So, in this droplet ejection, there is a transformation of the material from one form to the another form. So that is one of the key point which we have to observe. However, so the material will undergo a phase change. So when the material, when it undergoes a phase change, there is a chance that it may lose its property, or like the property may get changed from the thin film what we had created. So in order to avoid that, so there is a second technique which is available, which is called as a laser decay transfer. So in this laser decay transfer, what we are trying to do is, we are trying to introduce a sacrificial layer over here. So in this sacrificial layer, the laser beam is made to interact on the substrate with the sacrificial layer. The sacrificial layer will absorb the laser beam. A high pressure gas is created. This high pressure gas will result in expansion of the gas, and which will eject the pixel ejection. So as the pixel ejection moves, the the layer will try to get transferred over the printed structures. So when we try to manipulate this acceptor substrate and the donor substrate based on the, so we can get we can generate a different features. For example, if I want to create a line feature, so only thing what should I need to do is, so if I want to create a line feature something like this, I need to move this laser in this particular direction, and similarly I need to move this acceptor substrate in this direction. So what happens is, there is a kind of a pixel by pixel transfer which happens, which will result in printing of the structure in this particular domain. So by manipulating the donor region and an acceptor region along the 3 degrees of freedom, appropriately we can print any kind of feature size what we are required. Now the size of the feature plays a vital role. How the size of the features are controlled? Now let us take, in order to make a comparison with reference to the non-laser decay transfer and a laser decay transfer. So this is a kind of a setup which is used for a non-decay transfer. So in this non-decay transfer, there is an NDR laser, and then there is a variable aperture slit which is there, and then there is a prism arrangement and a focusing lens which is available. So what we are trying to do is, NDR laser is made to pass through the aperture slit and the prism through a focusing optics. This is the donor region and a receiver substrate. So here this is a kind of a non-decay transfer. So in this non-decay transfer, there is no sacrificial layer which is present over here, thus leading to the transfer of the material to the receiver substrate. Now these are some kind of features which are being generated in the non-transfer region. So this is a kind of a single spot, and this is a kind of a spot with spot overlap, and a line pattern using a cylindrical rod. So in the case of a single spot, if you see, like this transfer is happening in such a way that, like, the spot is ejected, that is the material is ejected from the donor region to the acceptor region, and we get a proper spot which is getting generated out of it. When these spots are overlapped, appropriately you get a line pattern coming out of it. When we try to use a kind of a cylindrical rod, so appropriately we convert the spot into a line to get a kind of a uniform pattern. Now the major limitation of this particular process is like phase change of the material, control of feature size, and the appropriate adhesion capability. So there is a chance that it may lead to a certain amount of defect within the ejected region if kind of air entrapment happened within the system. Now let us talk about the laser decay transfer based process. So in this laser decay transfer based process, so I would like to explain with reference to the preparation of the donor material towards the printing of the functional material. So the donor material is prepared. So in this particular case, we have considered a silicon wafer as a base material, and using a spin coating process, the sacrificial layer is coated. So the So here in this particular part, we may need to observe one important point. The donor material should be transparent to laser. However, the sacrificial the donor material should be transparent to laser. However, the sacrificial material should absorb the laser completely so that it can be helpful for ejecting the particle in the forward stroke. Now, this is a kind of a sacrificial layer which is coated on the silicon wafer and over the silicon wafer substrates. So, sputtering is used for coating. So, this is the overall configuration of a magnetron sputtering. So, since we are using a kind of an oxide in this, we are using an RF system to sputter the unit, and these are sputtered on the silicon wafer, and a surface profilometer is used for measuring the overall characteristics of it. Okay, so which is used for the measurement of the system, and then in order to study the characteristics, like there is a kind of a sputtering which is being deployed. Now we can see the construction of a micro 3D printer. So the features which we may need to print needs to be incorporated in the form of a CAD model. This CAD model is converted into a G&M code using an software interface, and this is a kind of an micro 3D printer which is being kept inside the glove box, since we are focusing more on the microelectronics or microsensor related applications. This is the overall configuration of the bending. So here there is a beam bender, a focusing lens, an acceptor substrate holder and a donor substrate holder. The material will transfer from the acceptor substrate holder to the donor substrate holder, resulting in deposition of the pixel with overlap. So here we have the control over the overlap. So we have a control over the pixel to pixel transformation, and there is a control over the kind of a lateral resolution and a substrate heating. So an indigenous development. In addition to this, the focal length and the spot diameter also plays a vital role. As discussed, so in this particular process, the donor region has 3 degrees of freedom and the acceptor regions has 3 DOF. Based on the donor region and acceptor region, appropriately printing can be taken up. Now, this is a kind of process which is evolved. A transparent substrate, a sacrificial layer, a donor material, a laser beam is made to interact, and then laser absorption happens on the sacrificial layer. A high pressure gas is created and the expansion gas forms, and it will result in transferring the material to the acceptor substrate. So this is the kind of features which is being printed over here, and this is the overall mechanism. So this system, this technology has a capability to print metal, as well as this technology also has a capability to print semiconductor materials and related areas. Now, some of the key aspect, if we try to look into it, is the overall ejection mechanism. This ejection mechanism plays a vital role in order to understand the overall pattern structure or the transfer of the pattern structure appropriately. So in this particular case, the pattern structure happens in such a way that it is because of the plume formation which gets evolved out of it. So with reference to this plume formation, if we observe, there is a main ejection mechanism which happens, and this ejection mechanism it will result in a kind of a deformation which sticks onto the surface, resulting in a kind of a textured growth. Now there are certain amount of in order to study the parameters. So one of the key parameter which is involved is the kind of a velocity. So because since the particle is moving at a very high velocity, this velocity, this moved particle will stick onto the surface, finally ending up in a kind of a pattern structures. So these are some of the different parameters and the different spots which are being created, or which are textures which are being created, which will give you a kind of a clarity how the parameters have an impact on the different points. So that is with reference to focal point, the beam can be manipulated, and appropriately each and every pixel transfer can be controlled. Then with reference to influence of laser fluence, there is a kind of a impact in such a way that the heat affected zones can be completely eradicated. With reference to a pulse flow overlap, the heat affected zones can be efficiently optimized so that we can have a continuous track and it can go for printing a large area structure. In fact, this technology, this microfabrication technology has a potential application in transferring selective layer by layer. For example, if this is a substrate, if I need to transfer a zinc oxide material at a particular point, this is possible using this laser decal transfer technology. So, only thing is, appropriately our manipulation head should have a higher resolution, and the acceptor and the acceptor region should have a higher resolution, and the donor region should have a higher resolution, and by keeping the laser fixed, so appropriately we can transfer the system. Now, these are some kind of different samples which are being prepared, and these are some kind of interdigitated structures which are being printed using this system. So, it has a capability to print multi-layer structures. In fact, it also has a capability in such a way that we can create a sandwich structures. For example, this can be a PDMS, this can be a nickel titanium, and over this again we can print a PDMS. So, this is one advantage with this particular system, where we can have a kind of multi-material and multi-layer printing using this technology. So, these are some of the printed structures which are being deployed in different devices, and as far as this microfabrication perspective point of view, this 3D printing microfabrication perspective point of view, it is a kind of a novel technology which uses the technique of micro 3D printing transfer for printing any kind of complex structures based on the requirement. So, this technology could print a micro antennas, a micro gear structures, a grid like of structures, as well as interdigitated structures, and these can be functionally or efficiently used. So, it is a kind of a maskless printing which is being demonstrated over here.
This is a plasma treatment setup. Here it have a vacuum chamber where it have a plasma gun where the voltage of high frequency in order of megahertz to gigahertz is applied, which ionize the gas present inside it. Here we place our substrate. After achieving a vacuum, we supply voltage and plasma is generated. This ionized particle bombard onto the substrate and cause physical and chemical modification. It can be used for surface cleaning and surface processing.